Welcome to all. This topic, application of group theory to hybrid spectroscopy. This topic is present in first semester chemistry syllabus of our university, Bharat University. This presentation is mainly for first semester students of our college, Qadir Mohin College, Adarampattinam. This topic is present in physical chemistry 1 paper, revised syllabus. In this syllabus, two examples are the one is water, another one is trans N2F2. So for these two examples, I have used the group theory, application of group theory to hybrid spectroscopy for these two molecules.
This slide shows a request to viewers.
First one is water molecule, H2O molecule. Group theory can be used to predict which molecular vibration is active in the infrared or Raman spectroscopy. And a molecular motion, that is total degrees of freedom, that is which includes translational, rotational, and vibrational. And the total number of degrees of freedom, that is given by the formula 3n, where n is the number of atoms in the molecule. For linear molecule, the number of molecular vibration, that is vibration mode, that is given by the formula 3n minus 5. And for nonlinear molecule, the number of vibration mode, that is given by 3n minus 6. So in the case of water molecule, the water molecule has 70 elements, identity element E, and a rotation axis C2, and sigma V xz plane and sigma V yz plane. And the molecule, the water molecule, belongs to C2V point group, which consists of these four elements. One is E, another one is C2, another one is sigma V xz plane and sigma V yz plane. And here the two planes, among the two planes, sigma V xz plane, that is a molecular plane. That is the plane which passes through all the atoms of the molecule. In the application of group theory to Raman spectroscopy, the number of unshifted atoms are first determined. In the case of water molecule, there are three atoms. What are the atoms? Two hydrogen atoms and one oxygen atom. So on operation of these elements, that is E, C2, sigma V xz, sigma V yz, the number of atoms unshifted are first determined. On operation of identity operation, no atom is shifted, so number of atoms unshifted is 3. Similarly, number of atoms unshifted on operation of C2, that is here the C2 which passes through the oxygen, which is on rotation of 180 degree angle, the hydrogen atoms are shifted, so number of atoms unshifted is 1, that atom is oxygen. And sigma V xz plane, that is molecular plane, on operation of sigma V plane, xz plane, no atom is shifted, therefore number of atoms unshifted, that is 3. And the operation of sigma V yz, that plane which is in between two hydrogen atoms, which passes through the oxygen atom, and on operation of this plane on this molecule, the hydrogen atoms are shifted and the oxygen is not shifted, so number of atoms unshifted is 1, that is oxygen atom. And now this number is multiplied by contribution by each atom to total character. Each element has its own contribution by each atom to the total character. So on operation on in the case of identity operation on multiplication of 3 and 3, that gives the total character, that is gamma 3n or gamma r or gamma total. Gamma 3n means that is representation corresponds to 3n degrees of freedom, and gamma r means that is representation which is reducible, so reducer representation, and gamma total means that is a representation corresponds to total degrees of freedom. So on multiplying number of atoms unshifted with the contribution by each atom to total character, we get the reducible representation, that is 3 into 3 9, 1 into minus 1 minus 1, 3 into 1, that is 3, 1 into 1 1. This representation is a reducible representation. Now this representation is reduced in terms of reduced representation of C2V character table. In the case of C2V character table, there are 4 classes corresponding to 4 classes. There are 4 representations. All are irreducible representations, and the irreducible representations are A1, A2, B1, B2. Now the reduced representation is reduced in terms of A1, A2, B1, B2 by make use of the formula, that is reduction formula, that is given in this slide, that is Ni is equal to 1 by H sigma G Gai IR, Gai I and Gai R. Gai IR means there is a character of ith representation of symmetry element R. Gai R means that is a character of reduced representation of symmetry element R. Here the symmetry element is not given. So 1 by H sigma G Gai I and Gai R. And here the H is the order of the group, that is total number of symmetry elements. In this case, there are 4 elements E, C2, sigma V XZ, sigma V YZ. So the order of this group is 4. 1 plus 1 plus 1 plus 1. That is equal to 4. So and by make use of this formula, reduction formula, the reduced representation is reduced in terms of A1, A2, B1, B2. And NA1 means that is number of times A1 representation occurs in the reduced representation. And the calculation is given, that is 1 by 4, 1 into 1 into 9 plus 1 into 1 into minus 1 plus 1 into 1 into 3 plus 1 into 1 into 1, that is equal to 3. Here in the first one, that is G value, and next value, that is a character of reduced representation, that is A1 representation, that is 1 1 1 1, and next number 9 minus 1 1 1, these are the character of reduced representation. So by this way, this reduced representation is reduced in terms of A1, that is equal to 3. That means A1 occurs in the reduced representation 3 times. Similarly, A2 is equal to 1. That means A2 occurs 1 time in gamma 3n, reduced representation. And NB1, that is equal to 3. That means this B1 representation occurs in 3 times in gamma 3n. And NB2, that is equal to 2. That means B2 occurs in 2 times in gamma 3n, that is reduced representation. Now the gamma 3n for water molecule, that is reduced to 3A1 plus A2 plus 3B1 plus 2B2. That is gamma 3n is equal to 3A1 plus A2 plus 3B1 plus 2B2. This slide shows the table which shows the contribution of symmetry operation by each atom to the total character. For symmetry operation E, the contribution is 3, and for C2, the contribution is minus 1, and for center of symmetry, the contribution is minus 3, and for symmetry plane sigma, the contribution is 1, and for other operations also, the values are given. That is the contribution of symmetry operation by each atom to the total character. The gamma 3n, that is equal to 3A1 plus A2 plus 3B1 plus 2B2. Totally, there are 9 modes of, that is 9 degrees of freedom. That is among the 9, 3 are translational and 3 are rotational. The remaining are vibrational mode. Now translation mode along x-axis, that is that has B1 character, along y-axis that is B2 character, and along z-axis that has A1 character. That is by seeing the third column of character table, we can easily identify the translation mode along x-axis and y-axis and z-axis. That is, a representation corresponds to the x coordinate, that is b1, that is b1 character, and representation corresponds to y coordinate y, that is b2 character, and the representation corresponds to the coordinate z, that has a1 character. So a1, b1, b2, these are the 3 translational mode. That is along x-axis it has B1 symmetry, along y-axis it has B2 symmetry, along z-axis it has A1 symmetry. So gamma translational, that is representation corresponds to translational mode, that is given by A1 plus B1 plus B2. Similarly, the rotational mode representation is also determined from third column of the character table. That is, a representation corresponds to Rx, that is B2, that is a rotation mode along x-axis, and Ry, that is a representation corresponds to Ry is B1, that is a representation corresponds to rotational mode along y-axis. Similarly, along z-axis, the rotation mode is A2. So gamma rotational, that is equal to A2 plus B1 plus B2. So that on adding these two, that is a translational rotational mode representation, we get gamma translational rotational mode, that is equal to A1 plus A2 plus 2B1 plus 2B2. Now on subtracting these translational rotational mode representation from gamma 3n, we get the vibrational mode, that is 2A1 plus B1. That is two vibrations have A1 symmetry and one vibration has B1 symmetry. This gamma vibration is equal to 2A1 plus B1. This slide shows the representation corresponding to vibration. In the case of water molecule, there are a number of vibrations: symmetrical stretching, asymmetrical stretching, and bending vibration. And here symmetrical stretching, that means that is equal extension or compression of bond. And symmetrical stretching has A1 character. After symmetrical stretching on operation of identity element C2 sigma V xz sigma V yz, we get the structure similar to original one. It is the final structure is indistinguishable with original one. Therefore, symmetrical stretching has A1 character. Similarly, symmetrical bending in plane, scissoring mode, has also A1 character. After scissoring mode vibration on operation of E, C2, sigma V xz, sigma V yz operations, we get the structure similar to original one. Therefore, scissoring mode has also A1 character. Another vibration, asymmetrical stretching. What is meant by asymmetrical stretching? Asymmetrical stretching means unequal extension or compression of bonds. And here, asymmetrical stretching has B1 character. After asymmetrical stretching, on operation of identity element, we get the structure similar to original one. Therefore, the character is 1. But on operation of C2, after asymmetric stretching, we get the structure which is indistinguishable, which is distinguishable with the original one. Therefore, that is -1 character. And on operation of sigma V xz after asymmetrical stretching, we get the structure similar to original one. Therefore, +1 character. And on operation of sigma V, y is at plane. After asymmetrical stretching, we get the structure which is distinguishable with original one. Therefore, the character is -1. Therefore, asymmetrical stretching has B1 character. So, symmetrical stretching and scissoring mode, these vibrations have A1 character, and asymmetrical stretching has B1 character. Each spectroscopy has its own selection rule. Now, what is selection rule? There is a rule which governs allowed transition. In the case of IR spectroscopy, IR spectroscopy is a vibration spectroscopy. During the vibration, there must be a change in the dipole moment and the transition moment integral, that is integral psi m psi vibration star d psi, that the integral should not be equal to 0. That is a selection rule for IR spectroscopy. In the case of polyatomic molecule, the change in dipole moment takes place in 3 directions, x, y, z. And hence the intensity depends on the 3 integrals. That is, integral has 3 components. That is integral psi vibration of mx, psi vibration star d psi. And another one is in the place of mx, my. Another integral is in the place of mx, mz. So we have 3 integrals. For a transition to occur, any one of these integrals should not be equal to 0. Should not be equal to 0. And then only the transition takes place. Then only the transition is, that vibration is IR active. For IR active vibration, any one of the integral should possess the symmetry of A1. This is symmetry selection rule. For the integral to be A1 symmetry, psi vibration star should belong to the same irreducible representations as M. The ground vibration level is normally A1, and the dipole moment vectors mx, my, mz correspond to the irreducible representation to which x, y, z coordinates. That is, mx corresponds to B1 character, and my has B2 character, and mz has A1 character. So, on substituting these psi vibrational as A1 and mx as B1 and psi vibration star as A1, and the product of these representations, that is A1, B1, A1, that is equal to B1. A1 into B1, that is B1. B1 into A1, that is B1. So as for this component, as for this integral component, the vibration A1 is IR inactive. In the case of second component of this integral, it is with the my, we get the direct product a1, b2, a1, that is equal to b2, that is a1 into b2, that is b2, b2 into a1, that is equal to b2, that is a direct product rule. So as per this component also, the vibration corresponds to a1 is IR inactive, but along the MZ vector, we get the product A1, that is A1 into A1 into A1, that is equal to A1. So as for this component, the vibration corresponds to A1 is IR active. For determining B1 symmetry has, that is vibration with the B1 symmetry, which is IR active or not, for that psi vibration star, that place is, that vibration star is substituted by B1 character, and in the first component of the second one, that is integral psi vibrational mx psi vibration star d psi, that is equal to A1 into B1 into B1. A1 into B1, the product is B1, B1 into B1, the product final answer is A1. So as for this component, this vibration corresponds to B1 character is IR active vibration. So the vibrations correspond to A1 and B1 are IR active vibrations. For water molecule, symmetrical stretching, which has A1 character, symmetrical bending in plane, which has also A1 character, asymmetrical stretching, which has B1 character, should all are IR active vibrations, all are active. In other words, for a vibration to be IR active, the representation corresponds to vibration should belong to the same species as one of the components of the dipole moment, that is mx, my, mz. So on observing third column, if the representation corresponds to either of x or y or z, then the vibration corresponds to that representation is IR active. In the case of C2 point group A1 and B1, these representations have the coordinates x, y, z, any of these coordinates. So these vibrations are IR active. For a transition to be Raman active, there should be a change in polarizability during the vibration, and the integral is integral psi vibrational alpha polarizability vector psi vibration star d psi. The value should not be equal to 0. So this integral has 6 components along x-axis, along xy, along xz, along yy, along yz, along zx, z. If any one of the integral is non-zero, then the vibration will be Raman active. For this, any one of the integral should be A1 symmetry. This is called symmetry selection rule. For a vibration to be Raman active, the representation corresponds to vibration should belong to the same species as any one of the components of the polarizability, that is alpha xx, alpha xy, alpha xz, alpha yy, alpha yz, alpha zz. That is, the representation corresponds to square of coordinates or product of coordinates. In the case of water molecule, A1 vibration corresponds to x square, y square, z square, which is observed from fourth column of character table, and B1 vibration corresponds to the binary product xz, and hence all are Raman active. So in the case of water molecule, symmetrical stretching vibration, symmetrical bending vibration, these have A1 character, and asymmetrical stretching, which has B1 character, all are IR active and Raman active, because these representations have the coordinates xy, xyz or the, and the square of coordinates. Therefore, these are two A1 and B1 representations. The vibration corresponds to these representations are IR and Raman active. The next example is trans N2F2 molecule. This molecule has 4 atoms. The total degrees of freedom, the formula is 3n. And the for linear molecule number of modes of vibration, that is 3n minus 5. This molecule trans N2F2, that molecule is non-linear. The formula is 3n minus 6. So total number of degrees of freedom, that is 3 into 4, that is vibration mode, that is given by 3 into 4 minus 6, that is equal to 6. So this molecule has 6 vibrational mode, and this molecule belongs to C2H point group, and the symmetry operations of this point group, the collection is E, C2, center of symmetry I, and sigma H plane. And the plane of the molecule, that is lies in the XZ plane, that is a molecular plane, that plane is sigma H plane. So the molecule has the symmetry operations, identity operation, another one is C2 operation, another is center of symmetry, inversion operation, another one is sigma H plane, that is symmetry plane, that is perpendicular to axis of symmetry. So these are the symmetry operation of this molecule, trans N2F2 molecule. As in the previous example, here also number of unshifted atoms are determined on operation of identity operation and C2 operation and center of symmetry operation and sigma H plane operation. Number of atoms unshifted during operation of identity operation, the number is 4. So no atom is shifted during operation of identity operation. So total number of atoms is 4. So therefore number of atoms unshifted is 4. And on operation of C2, all the atoms are shifted. That is, nitrogens are interchanged and hydrogen also interchanged. So the number of atoms unshifted is 0. Similarly, on operation of center of symmetry, the number of atoms unshifted is 0. And on operation of sigma H plane here, that is molecular plane, during the operation of sigma H plane, no atom is shifted. No atom means two hydrogen atoms and two nitrogen atoms. No atom is shifted, therefore number of atoms unshifted is 4. And in the previous case here also, the contribution by each atom to total character for identity operation, the contribution is 3, and for C2 operation, the contribution is -1, and for center of symmetry, the contribution is -3, and for sigma H plane, the contribution is 1. So on multiplying number of atoms unshifted with the contribution by each atom to total character, we get the total character representation, that is gamma 3n, that is gamma r, otherwise gamma total. So 4 into 3, 12, 0 into -1, 0, 0 into -3, 0, 4 into 1, that is 4. Now this representation, this reduced representation, this representation is reduced in terms of irreduced representation of C2H character table, C2H point group. The representations are, irreduced representations are AG, PG, AU, BU. Now gamma R is reduced in terms of AG, PG, AU, BU by making use of the reduction formula. The formula is given and the calculation is also given, and the number of times AG occurs, the reduced representation is 4, and number of times PG occurs in the reduced representation as the answer is 2, and number of times AU occurs in the reduced representation, that is 2, and the number of times BU occurs in the reduced representation, that is 4. That means gamma 3n for trans N2F2, that is reduced to 4AG plus 2PG plus 2AU plus 4BU. That is the reduced representation in terms of irreduced representation. That is, the reduced representation is in the form of reduced form. Gamma 3n for trans N2F2, that is reduced to 4AG, 2BG, 2AU plus 4BU. That is gamma 3n is equal to 4AG plus 2BG plus 2AU plus 4BU. Now the translation mode along x-axis, that is BU symmetry, along y-axis BU symmetry, along z-axis AU symmetry. These are determined from third column of C2H character table. Now that is the translational representation corresponds to translational mode, that is equal to AU plus 2BU. Similarly for rotational mode along x-axis as BG symmetry, along y-axis as PG symmetry, along z-axis as AG symmetry. This is also These are also determined from third column of C2H character table. Therefore, gamma rotational is equal to Ag plus 2Bg. And on adding these two, that is representations corresponds to translational and rotational. That is equal to Ag plus 2Bg Au plus 2Bu. On subtracting this from gamma 3n, we get the vibrational mode, that is 3Ag plus 1Au plus 2Bu. The six vibration modes are uh, 3Ag and plus and 1Ag and 2Bu. For a transition to be IR active, that should be a change in the dipole moment, and the transition moment integral value should not be equal to 0. This transition moment integral has three components along x, mx, my, mz, and if any one of the above integral is non-zero, the vibration will be IR active. For this, any one of the integral should be Ag symmetry. Now, this is symmetry selection rule. The dipole moment along x-axis has Bu symmetry, along y-axis Bu symmetry, along z-axis Au symmetry. These are determined from third column of C2H character table. And the representations Au, Bu, these representations belong to coordinates and not to the square of coordinates. Therefore, the vibrations corresponding to these representations, that is Au and Bu, are IR active and Raman inactive, because these two representations correspond to not to square of coordinates or product of coordinates. Therefore, these vibrations corresponds to these two representations are Raman inactive. For a transit to be Raman active, there should be a change in the polarizability during vibration, and the transition moment integral should not be equal to 0. Now, this integral has six components, that is along x-axis, xy, xz, yy, yz, zz. If any one of the integral is non-zero, then the vibration will be Raman active. For this, any one of the integral should be Ag symmetric. This is symmetric selection rule. For a vibration to be Raman active, the representation corresponds to vibration should belong to the same species as one of the components of the polarizability, that is alpha xx, that is alpha xy, alpha xz, alpha yy, alpha yz, and alpha zz. In the case of trans N2F2 molecule, the total vibration mode, that is 3Ag, 1Au, 2Bu, three representation Ag representation corresponds to square of coordinates, that is x square, y square, z square, and the product of coordinates xy, and not to the single coordinates x, y, z. So and so the vibration corresponds to Ag representations. Ag representation are Raman active and IR inactive. So three Raman absorption are obtained due to the vibration correspond to Ag symmetry. Thus, in this case, trans N2 molecule, trans N2F2 molecule, three IR and Raman absorptions are obtained, but IR active vibrations, that is Au and Bu, are Raman inactive and vice versa. This is called mutual exclusion principle. That is, for a molecule with a center of symmetry I, IR active vibrations are Raman inactive and vice versa. These are about application of group theory to vibrate spectra of water molecule and trans N2F2.
I express my sincere thanks to all viewers, and also I want to get positive and negative comments from viewers. That makes me the future lecture in a better way. Once again, I thank one and all. Thank you.